ways to get it to him before, but none of them were effective.
So frustrating that you were saying you waited 20 minutes and then it was like actually
it was literally 20 minutes loading onto Canvas. It let it load for 20 minutes, and then once like the bar got full, it said there was an error.
That's the worst.
And I was not about to wait another 20 minutes just for it to say the same thing.
All right, can we double check my field where I am?
Yeah. You've got like to the edge of that board, yeah, where your hand is,
Okay.
to like the middle of that board.
Okay, cool. Good to know. All right. So we definitely are seeing interference. We know what's happening. I proved it to you, right? Shows you a picture. But that's not the only place it happens. And something else I want you to think about is this. Like, why don't we see that right now? Why aren't we seeing bright and light and dark spots from these lights that are coming at us?
Because the lights coming at us are every wavelength.
Okay, well, they could have multiple wavelengths for sure, right?
not being shined through a slit either.
True. The shining through the slit was really just so I could make two sources of light. Right? That was the whole point of that, is just to like make it so that it's as if there are just the two sources coming out.
They're also not like a laser point, it's like spread out.
Yeah, so here's the reality. There is interference going on. However, there is so much, so many different waves coming, so many different places, that the likelihood that everything gets canceled out exactly is virtually zero. And even if it does, it's going to be so shortly lived. And then you throw in the fact that we've got different wavelengths. If you look at that formula, pull it back over here.
Yeah, because isn't like white light or like the light coming out like all the wavelengths? Isn't that how that works?
Not these lights.
Oh.
We'll talk about that later.
Because these are LEDs.
As he chuckles. Well, it all depends upon what's actually creating the light. We'll talk about this later. We got to get some quantum physics under our belt before we can get to that.
Mm-hmm.
But if you come back to this one, right? Remember how we had our light and dark spots and their locations? A big part of it was based on wavelength. And so if we've got a bunch of different wavelengths, those things are going to overlap. Well, think about like that bright dark interference. Imagine you got that overlaid with a whole bunch of other interference patterns. Even if we were getting interference like that, those still would kind of make it so that it's not ever completely dark, right? So it's a bit deeper than that. It's definitely a bit deeper than that, but primarily because we've got lots of sources of light, not just two. So we've got lots of waves coming together that are not that are overlapping. One other thing I want you to realize is that when we saw that pattern, you notice how that pattern kind of terminated eventually? It didn't go forever. And there's a reason for that. And it's not just small angle approximation. Take a look at this just real quick with the constructive interference. This has got a sign in it. If I rewrite that with sign, it's equal to n lambda over d. Well, remember there's a maximum amount that we can get from sine, right? The biggest is that it can equal 1. So no matter what, that can't be larger than 1. And if I just run the numbers on that real fast, or do a little bit of algebra real quick, that shows us that the n is going to be limited. There is a maximum number of bright spots that we can get. It's going to be dependent upon the width of the slits, the width between the slits, and the wavelength of the light. So if we had done that with our, like, let's just see what that would have been if we had done 750 nanometers, or no, 650 nanometers. And what did I tell you the D was, like 0.25?
It was like
Hold on.
times 10 to the negative fourth.
Let me pull it back up here again. So it's 0.25 millimeters. So 2.5 times 10 to the minus 4. Right? So if we run the numbers on that, we're going to see that there is a maximum number of fringes that we're going to see.
It's gonna be a big number.
Let alone the fact, yeah, in this case it's going to be pretty big, let alone the fact that eventually small angle approximation doesn't hold. But no matter what, at some point, this pattern is going to die out just because of, math. Right? Eventually, the angle gets so large that the angle isn't there anymore, is basically what that's saying. All right, anyway, so interference definitely happens. This might feel like a really fabricated, made up kind of scenario to see it. Kind of, yes. It's a great demonstration, so you can really see it. But there are going to be other places where we see this interference, and I'll show you how you can see this just with your hand after we talk about diffraction. Yeah, you know me, I gotta have my hook for you to come back later. Okay, well, but this isn't the only place that we see this. There are other places that we get interference. So how about this? You ever gone outside after the rainstorm and you've looked at, you go to a parking lot and you see swirly rainbow colors?
Yeah.
Like oil.
Yeah, like on the oil. Or how about when you blow a bubble, soap bubble, right? You're washing your dishes and so, and the light hits it just right and you see all the little swirly colors. What you're actually seeing there is interference. And this we call thin film interference. So let's talk about that for a bit. So like always, this is exactly what it sounds like. This is interference that's being caused by having a very thin film of material. Whether it's oil that's sitting on top of water, whether it's the soap bubble or whatever. Basically, here's our picture. We've got our little film of stuff. So let's actually look at the oil on water thing. So when you're out in the parking lot after it rains and you see those swirly colors where oil has gotten on top. Okay, so basically in that situation, we've got air, oil, and water. There's just a little film of oil on top of the water. Or if you want to talk about like a bubble would be like a soap bubble, would be, we've got air, then we've got the soap, and then we're back to air, right? But regardless, we just got this little thin film of stuff. All right, so what's causing this? Well, it's really reflections. Because here's what happens. Suppose we're looking at the air, oil, water thing. Sunlight comes down and hits the water, and it's going to do two things, right? At every interface, it's going to reflect some, and it's going to pass through some if this material allows light to pass through. But oil, like the little films of oil we see there, definitely allow that. Okay, so there's going to be reflection, and then there's going to be refraction. Now, what happens at this interface?
It's going to reflect and refract.
Same thing, there's going to be reflection, and then when it comes up here, it'll be parallel. It refracts parallel because of Snell's law, but it'll be offset just a little bit, right? And then there's also more that goes down into the water. I don't really care about what happens down here. Because most of that light does not come back out. It's going to get absorbed by the dark pavement and that sort of thing. Okay. Well, let's just think about this. Now, if I send in light of a certain color, so imagine I'm shining a laser beam onto this. These two refracted rays are going to interfere with each other because they're the same light. It's just one of them has gone a little bit further through the oil and come back out. And so it's these two working in conjunction that interfere. And the air, so like a bubble, a soap bubble, is exactly the same, right? There's going to be a refraction, and it's going to pass through, but this is going to come out. So it's exactly the same idea. It's just I might care about light that goes through that, depending upon what's going on. But in terms of the interference, it really is just going to be the reflection. Okay, so we have really the same thing as before. If they are in phase, then it's going to be super bright. And if it's out of phase, it's going to be super dark. All right, so the question is, how can we tell what's going to be in phase and what's going to be out of phase, and how do we calculate that? Well, we're just going to have to do a little math. But it's probably not going to surprise you that it depends upon the wavelength. If that does surprise you, once we run the numbers, you'll go, oh yeah, that makes sense. But that's why sometimes when you're looking at a soap bubble, it looks red, sometimes it looks pink, sometimes it looks green. It just depends on the wavelengths that are actually getting constructively interfered. When you see bright colors, that's constructive interference. All right, now, before we get into it though, I need to remind you something else about waves, and that is what happens when waves reflect. Sometimes they get out of phase when they reflect. Sometimes they stay in phase. Did you talk about this? Do you remember talking about this last year?
I vaguely recall.
All right, so there's a vague notion of maybe something along those lines. Okay, well, when you've got a physical wave, like let's say I've got a string, and I attach that string to the wall, and I send a wave down. So, I just like throw it upward and let it down so there's this peak going. When it hits the wall and returns, it actually returns on the underside of the string. So I'm seeing some head nods, like you kind of remember something happened along those lines. As opposed to, let's say that string was attached to like a ring that's around a pole, and I let that go, then when that ring goes up and comes back down, that wave is going to return in the same orientation as how I sent it. So reflections of waves kind of depends what goes on. Well, light is no different. Light is no different. And in terms of what happens in terms of phase changes, it all depends upon n. It all depends upon the index of refraction. And here's the best way to think about it. Like I was saying, so like when you send a wave at a wall, if it comes in, oriented upward, it returns oriented downward. Because that wall is really rigid, doesn't allow that wave to move. So as it reflects, it kind of gets thrust back the other direction. And then the other one I was talking about is like if you've got a pole with like a ring on it. And this one, if you send it in with an upright orientation, it returns with a similar upright orientation. And that's because this ring isn't holding it back. The wave can just go and move. So it literally will move that thing up, and then as it comes back down, that sends the wave back with that vertical orientation. Okay, so that was the deal with physical waves. Well, with light, Same thing happens in this case if we are going from small to big N. So if you're going from smaller to bigger N, you are going to get a reflection that's out of phase. And then the other one is vice versa, right? Where we're going from bigger to smaller. In fact, that's something I think I wrote here. Yeah, I've got the other way around. This is from big to small. All right, so it is possible, just because of reflections, we can be now out of phase. All right, but there's also a little bit more going on here with thin films, not just this reflective stuff. Now, I just want you to notice that these are two different scenarios. Like this one where we're going from air to soap and then soap to air. One of those reflections is going to be in phase and the other one's going to be out of phase. Right? Because we're going from smaller to bigger to smaller. This one, since it's smaller to bigger to even bigger, the reflections that happen with both of these are actually going to be in phase with each other. Because they're both going from smaller to bigger N. So they both react exactly the same way. So when we are looking at these, when we're doing thin film interference, what you really want to look at is what's happening on the two ends. On the two ends of the film. Are both of those reflections getting out of phase, or are both of them the same? Right? Because part of that is going to take into, or is going to be necessary to figure out whether we have interference or not. Okay, but that's only part of the story. We have to worry about that, but we also have to worry about this extra distance. And this is where it gets similar to the two-slit interference pattern. Remember what caused that two-slit interference was the fact that each of the rays went a different distance? Well, this is extra distance that one of those rays travels that the other doesn't. So let's go to this, like thinking about this one, where both reflections are in phase with each other. In that case, if this extra distance equals a whole number of wavelengths, then we're going to have constructive interference. So we really are going to have to look at this material and go, all right, how many, like because of its thickness, how many wavelengths happened? If it ends up being a whole number, then we're going to get constructive interference. Now think about this one. Because one reflection led to a out of phase and the other one didn't, they're already out of phase. So in order to get constructive, this extra distance has to be off by a half of a wavelength. So this just complicates it a little bit more. It's very similar to what we did before. We're looking at that extra distance. But now it's not necessarily that the extra distance is a whole number of wavelengths. It might be that it's only a half number of wavelengths. The depending upon how the ends are related to each other.
Wait, for bottom, that's for destructive?
Nope, for constructive.
Okay.
Because the reflections, like if we look at number 1 versus number 2, number 1 and number 2 are already going to be out of phase because of reflection, since one went from smaller end to bigger end and the other one from bigger to smaller.
Got it.
So they're already going to be half of a wavelength out of phase. To get constructive, we got to get it back into phase, which is by doing an extra half wavelength. As opposed to these two, those two both have the same kind of reflection going from smaller to bigger end. So when they came off of reflection, they were in phase. So we just need to keep them in phase by using a whole number of wavelengths. Okay, so it's a little bit more complicated because now just the extra distance traveled, that's only part of it. The other part is we got to look at reflections. Okay, well, you want to make this even worse? The wavelength of the light changes when it moves into a different material. Now, I don't think we've talked about this. But let's think about why that must be. So how do you determine wavelength? From waves, like back in the day when you were talking about waves and wavelength and speed and all that good stuff. Do you remember how they were related?
Was it 1 over the frequency?
So the wavelength is 1 over the frequency. And then how did you calculate frequency from speed?
No, I don't remember.
Okay, so in general, that's okay. I appreciate the fact that you remember that it was 1 over frequency with the wavelength. Right? But think about what wavelength is in. That's in meters. It's a length. Frequency is a per second. And so for light, C is equal to lambda times F. So the speed is equal to lambda times F. Okay, but we know that speed changes when you go into a different material, right? But the frequency of the wave is still the same. Like, think about it. So here's our change in material, and we're sending the wave in. So it's got whatever its frequency and its wavelength. Now, the frequency of the waves hitting this boundary is the frequency of the wave out in, let's just say that's a vacuum. Well, those waves leave this boundary at the exact same frequency. They don't bunch up. Right? It's not like they just all get stuck and compressed. It's just, well, they're just moving away slower, but they're still moving at the same, like here comes a wave in and it immediately goes out, just slower. Comes in, goes out, comes in, goes out. So it turns out that the frequency stays the same. They just slow down. So if they slow down, that just means that they're going to get closer to each other. So what happened to the wavelength? It got smaller. Okay. So it turns out that the frequency is the same. So the frequency is constant. And so the speed must decrease, or lambda must decrease when the speed decreases. So if we go into a bigger n means we're going slower, which means our lambda is going to have to go down. Okay, well, by how much? Well, this is where we go back to how n was defined. How did we define n? Like when glass's n is 1.5, what does that mean?
That means light is 1.5 times slower in it.
Yeah, it was the ratio. It was the ratio of the speed of light in a vacuum compared to the speed of light in that material, right? So whatever that n is, it's a factor of the speed. Okay, well, if we need frequency to stay the same, and we affect the speed by a factor of n, we affect lambda by that same factor of n. So in a material, so in any kind of a medium, I'm going to call it lambda sub n. So this is the wavelength in that material. It's actually equal to the wavelength, I'm going to put it sub c, meaning for when we're in a vacuum, divided by that n. So this is something else we're going to have to take into account. Because as soon as light enters, goes from air into oil, the wavelength in oil is different than the wavelength in the air. And that's going to really matter if we need the distance traveled to be equal to a whole number of wavelengths. If we base it on wavelength out in air, that's going to be the incorrect distance because it's not the right wavelength in the material. Okay, so here's what we're going to have to do. We're going to have to think about this extra distance. We're going to look at this extra distance, and we're going to have to see, are we a whole number of wavelengths in this material? Okay, so I think what's going to be best is let's do a specific example where we've got some ends and all that, so we can talk about reflections, whether or not they're in phase with each other or out of phase, so that then we can kind of figure this whole thing out. Okay, so for this example, let's look at like my eyeglasses. I have special eyeglasses that have a anti-reflective coating on them, right? It just helps keep reflections from happening. In essence, it's a little thin film. It's a very thin film of material that is going to help counter reflections, meaning lead to destructive interference for wavelengths that are kind of in the center of the visible spectrum. Okay. So what that looks like would be something like this, where we've got our thin little film on top of glass. So here are my eyeglasses, and here's that anti-reflective film, and then we've got air. Now, in order to actually do anything with this, we got to know ends. We have to know the different ends of the different materials for two reasons. One, we need to know about reflections, right? Are we going from bigger to smaller or smaller to bigger? We got to know those. But then we also especially need to know N of the material that's that film, because that's going to determine their wavelengths, which then we're going to need to know. Okay, so here are some N values for you. Air, of course, we're going to go with N equal 1. Glass, we'll go with 1.5. And then this film, let's say that it's got an N of 1.38. Okay, so here are our two rays that are going to interfere. So there's the first one that comes and just reflects off the surface. Then I'm going to do a different color. This one, black. So there's the one that's going to come in, refract, and then reflect, and come out. Okay. So that red and that black are going to interfere. So first things first, look at the reflections. Look at the two reflections. Are those two reflections going to be in phase with each other or out of phase with each other? So just look at the ends. The first one, we're going from an n of 1 to 1.38. So we're going from smaller to bigger. And then what about the black one? It's reflecting from film to glass, which is exactly the same situation. So both of those reflections are going to be the same type of reflection. So that means that they're going to be in phase with each other. Okay, so I'm just going to make a note of that the reflections are in phase with each other. All right, so if I want constructive interference, that means that the extra distance traveled has to equal a whole number of wavelengths. Since they're already in phase with each other. If I want destructive, that extra distance has to be some whole number plus a half of a wavelength. Okay, so first thing I always figure out is look at the reflections, are they in phase with each other or not? Okay, so now suppose I was looking for constructive. So what I need is that extra distance traveled to equal n times lambda. Oh, let's not do n. Do m times lambda. Because n is the index of refraction. So it's a certain number of wavelengths. Times lambda. But I'm actually going to put here m times lambda n. It needs to be a whole number of wavelengths of that light when it's in the film. And then similarly for destructive, I need that extra distance to equal m plus 1/2 times lambda. But this is very similar to what we did last time, right? When we were looking at the double slit experiment. Just a certain number of wavelengths. Okay, so what is that extra distance traveled? How much further does the black ray go than the red ray? It's got to go all the way down through the film and then turn back and come up through. So that extra distance is roughly twice the thickness. And that twice the thickness is probably a really good approximation if we have small angles, like we tend to do, right? So what we're going to say is that extra distance, this is going to be approximately twice the thickness. So let me give a value for that thickness. Well, let's just leave it as a generic for a second. Let's just say that this thickness is about L, capital L for a length. So if I want constructive interference, this formula is starting to look useful. It's going to be 2 times L is equal to M times, and I'm just going to change that lambda to lambda over N, the N of that material. And same thing's going to have a very similar thing for destructive, just equals M plus 1/2. Okay, so let's do this. Let's say that we're going to design this so that it destructs, so it destructively interferes a specific wavelength. And let's target kind of in the middle of the visible spectrum. What kind of wavelength is in the middle, roughly?
Like 750, 720 range.
That's on the high end. That's the reds. So,
Is it bigger than that?
so the reds are like, the max on the reds are 700-ish. Anybody remember the mins with the purple?
I thought purples were bigger.
Yeah, the bigger frequency, smaller wavelength.
Yeah.
They're around 400. Okay, so purple's around 400. The bottom, maybe about 380, somewhere in there. And then the reds cap out around 750 or so.
So let's call it like 450.
So if we're in the like
550.
like 550, 575, somewhere in there, it's going to be kind of in the middle. Okay, so here's what we're going to try to do. Let's try to destructively interfere 550 nanometers. And my question is, what's the what thickness of coating, what thickness of this film will make it so that we destruct that? So we're going to try to, let's determine the thickness. Needed to destructively interfere 550 nanometers.
You just wrote 500.
Thank you. So that's in the greenish yellow kind of realm.
So we need to figure out what N in the film is for that color.
Okay. So let's just do this. We're going to destructively interfere. We need to use this bottom guy because both the reflections were in phase with each other. So we need to be off by a half number of wavelengths in the material. So we're going to have that 2L is going to equal M plus 1/2 times lambda over N. So I can divide by 2. So we're going to get lambda over 2N times M plus 1/2. Yeah.
Do we need to figure out the N for that frequency, or can we just say negligible and move on?
Okay, the fact that different colors have different ends
Yeah.
because of dispersion, no, we're just going to go with this end.
Okay.
Technically, yep, we would have to account for the fact that this one's going to have a slightly different value than others, but it's going to be pretty negligible, plus, like,
Perfect.
you know. But yes, technically we would have to worry about it. And I bet that folks that produce these kinds of things worry about that. Although we are only shooting for a representative wavelength anyway. Okay, well maybe then if we don't account for that change in N, it's really we're knocking out 538 nanometers instead of 550, which is still kind of where we need to be. Okay, so notice then that there are lots of thicknesses that are going to make this work. Because I can have the extra distance is 1/2 of a wavelength. It could be 1.5, 2.5, 3.5, 4.5.
I reckon you want the smallest one.
So probably we want to shoot for the thinnest, mostly because especially if this is a business venture, that's less material we have to use and all that. But and maybe we can't be that precise. But let's try the thinnest.
N
Okay.
equals 1. Or N equals 1.
That's actually not the thinnest.
M equals 0.
Yeah, so the thinnest is going to be when M equals 0. Because then we're only off by 1/2 of a wavelength. So if we let m equal 0, then that thickness is going to equal 550 nanometers divided by 2 times 1.38 times 1/2. So this is going to be thin. I mean, look at it's going to be on the order of hundreds of nanometers. Because 1.38 times 4
It's going to be
is 6.
99.6 nanometers.
Yeah, so just under 100. Would you say 90.6?
99.
99.6?
Call it 100.
So it's actually very thin. Not a lot is needed to make that happen.
What is the M again?
So m is the number of wavelengths. So m is, this guy is just a number of additional wavelengths. In the other formula, I called it n. I switched it to m because now n is index of refraction. So basically, by setting m equals 0, I'm just saying, well, as that light passes down and back, it goes through 1/2 of a wavelength. So that 1/2 of a wavelength now cancels. Okay, so this is how we can start making things so that when they reflect, they're actually interfered with and we don't see the reflection. All right, but let's do a follow-up on this. Suppose we make it this thickness. What wavelengths are constructively interfered? Right, we're targeting the greenish yellow of 550 nanometers. Obviously, there are going to be other wavelengths that constructively interfere. Let's see if we can find those. So, nothing's going to change here, but now let's look at constructive. I already have my thickness, and what I'm looking for is my wavelength. So if I rewrite that equation for lambda, lambda is going to equal 2nl over m. So there are going to be many wavelengths
Any multiple
that do this.
275.
Right? It's going to be, we've got 2 times 1.38 times 550 divided by m, which is going to go from 1 to 2 to 3 to 4 to 5 to 6 to 7 and so on.
You missed L, right?
Oh, sorry, yeah, L was the 99.6. Thank you. Right, we're going with a thickness of 99.6. All right, so let's start making a list. So here will be wavelength 1. 2 times 1.38 times 99.6.
275.
275. So that wavelength of light is actually going to be constructively interfered here, which means it would be nice and bright. What color is that? It's a trick
Not
question.
one we can see.
Yeah, it's not one we see. Visible light goes from like 400 to 750. This is ultraviolet. It may actually even be below ultraviolet, I'm not really sure where the cutoff is for ultraviolet to smaller wavelength. But that one we're definitely not going to see. Okay, well, what if
Smaller it gets.
we go to lambda 2? So if we let m equal 2, Well, it's going to be half that big. So 137.5 nanometers, which also we can't see. And if we keep going, like they just keep getting smaller and smaller and smaller. So this coating would actually be very effective because nothing is going to look really bright as it reflects. If you are going to see colors off this reflection, they're going to skew towards the ends of the spectrum. So you might see some red, you might see some blue. All right, does anybody have reflective coating lenses? I wonder if we can actually see this with my glasses. Because sometimes you can tell somebody got them. Because if you look at them and oh yeah, you totally can. All right, so I apologize for y'all because I don't know you're not gonna be able to see it. But if you look at the reflections of the light through my glasses, do you kind of see it? Kind of looks like kind of bluish, or maybe a little like pink even. So think about that. If you see the blue, well, that's the blue-purple side of the spectrum. If it looks a little pinkish, that's that red side. And even if you can combine them, it kind of looks like a little bit purplish. So you can tell 100% if someone got this. If you've got other glass that is not like that is not reflectively coated, I don't see anything in here. Like just take like a water glass, right? Like that you've got in your kitchen, and look at the reflections of light. You will not likely see them skewed like that. You might get a little bit because of the thickness of the glass, because now the glass itself is acting like a thin film. But anti-reflective coatings, you can always tell. And it's really funny because I am how I am. When I'm talking to someone, I'm always paying attention to that. I just find it amusing. Like, ooh, I know what kind of glasses you have. Here. All right, so there's an example where they were already in phase when they reflected. So let's do one where they're not. And let's look at the bubble of soap. So we'll go and look at that example. And a bubble of soap, this is now where we're going to go from air to soap back to air. Soap bubble. So we got air, soap, and then air. And in terms of the ends, obviously the air is n=1 on both sides. We're assuming that the air inside the bubble is not different than it was on the outside. And then for the soap, let's go with 1.33. So same situation, we got the two rays coming in. The black one that just bounces right off. And then we got the purple one that passes through and then comes back and bounces. All right, so now this time, the first reflection goes from small n to big N, and the other one goes from big to small. So that means those two reflections are out of phase. So based on nothing else, they're already out of phase when they're coming out. Okay. So in this case, we've got the reflections are out of phase. Now, what that means is that the exact reverse happens for constructive versus destructive. Now, if I want to have destructive interference, how many wavelengths have to happen in the film?
One. You said destructive?
Yeah, for destructive.
One.
Yeah, oh, how about a whole number? So 1, 2, 3, about a whole number? As opposed to before, a whole number led to constructive interference. All right, so this is why you got to pay attention to that. So now constructive means m plus 1/2 wavelengths, and destructive is a whole number, so m times lambda. All right, so here's my question. Is suppose that I tell you the thickness, let's say that the thickness of this is 320 nanometers. My question is, what color do we see?
Whatever is constructively interfering.
Okay, so if it's something we see, it's going to have to be present, so it's not destructed, it's going to be constructed. So we're looking for constructive interference. What wavelength is going to lead to constructive interference? Well, it's really exactly the same thing that we just did. If we go, all right, that thickness, 2 times that thickness, to get constructive interference, we need to be off by 1/2, so m plus 1/2. And then, again, this is going to be the lambda over n. So I'm solving for n, or for lambda. And I want to solve for lambda, not lambda n, because we are in the air, looking at this light in the air. So we're going to do it with an n value of 1. All right, well, again, there are lots of different wavelengths that do this. Because like if I just start with m equals 0, that lambda is going to be 4nl. Because when m is 0, I'm dividing by half. That's 4nl. But there's also going to be when m is 1, that's going to be 4/3 nl. Because 1 plus 1/2 is 3/2, and 1 right? And then the next one, when m equals 2, that's lambda equals 4/5 nl,
567.
and so on down the line. Okay, so 567, that's the first one.
That's the second one. The first one we won't be able to see.
What was the first one?
That's going to be 1,700, I think.
Okay. So if we do the first one with m equals 0, you get a wavelength of 1700 nanometers, which is definitely out of our visual range. Okay, so then when we plug in 1, you said that was the 5 something?
567.
567. All right, and then if we go to the next one, that's going to be on the order of 3 something?
340.
340. And then they're going to continue getting smaller.
Can we see 340?
All right, so 340 is below what we're going to see. Probably. It's going to kind of depend.
So we're going to see like yellow green.
Some people's eyes are such that they probably can see 340. But that's going to be people that are kind of on the, like if we have sort of like a normal distribution, they're going to be people that are over on the edge. Right, so most people, I was going to say regular, that's not the right word, but standard human probably does not see 340. No human's going to see 1700.
I don't know. I'm built different.
Okay, maybe some sort of like X-Men mutant style, maybe.
I'm built different. I can see it.
You're built different, you can see 1700?
Yeah.
What's it look like?
Chill.
Chill? It should actually be the opposite. It should be, because it's infrared, it should probably be a little bit not chill. Okay, so most likely, what we're going to see is 567, which is going to be on that yellowish, probably the yellowish end of green. Right? So actually not that different than the one that we started with the other example. And even if both of those are coming out, most likely you're going to see, and you can see 340 in general, you're still probably going to see the 567 because we're more attuned to seeing that color. Okay, so this soap bubble at this point would look kind of yellowish. What would we have to change about it to make it look red?
The thickness.
Yeah, if you change that thickness, if we make that thickness just a little bit thicker, then that number scoots up and it's going to look red. What if we wanted to make it look blue? Decrease that thickness. Or potentially increase that thickness, but then it's one of the other characteristic guys, right? Like it's this one that starts turning blue or whatever. But the point is you got to change the thickness. So if you've ever had a soap bubble and really looked at it, you notice how the colors all kind of swirl?
Yeah.
It's changing colors all the time.
Not consistent
So
thickness.
it's like different thickness.
It's the thickness of that bubble is changing. Yeah, if you want to have some fun, just kind of experiment with this. Get a bubble, get a soap bubble that's like that you can, maybe your finger's not going to work because it might pop it, but it's dangling off something. So dangling off a spoon or something. Watch it, and you'll see the colors changing. And the reason that it's changing is gravity is pulling all that film towards the bottom. So it's thinning it out on top and thickening it on the bottom. And it's also not uniform because that film is kind of sliding around and that's why it looks like swirly colors. Or after the rain, when you go into the parking lot and you're looking at that oil, it doesn't always look, oh, it's all purple. No. So it's purple, so it's red, so it's green. Same reason. It's the thickness of that oil is varying. And so we're seeing different constructive interference. Sometimes it looks blue.
So if you move a bubble with no gravity, would it be the same color everywhere?
Assuming no other forces acting on it, yeah.
With the bubble?
But like if you start like blowing a bit, you might, cause it to build up in certain places or not. So yeah, it'd be really interesting if you had a bubble in the space station and then you made sure that that bubble was like in a vacuum or something like that. Although as soon as you try to make a vacuum, it's going to destroy the bubble. But like, so if there was no, like your breath wasn't on it, the circulating fans or anything, it should
Consistent.
end up being consistent color. I never experienced that because I don't live in the space station. All right, so another place interference happens. Okay, we're gonna call it a day because it's it's 10 till. So we will continue this discussion next week, and we'll also start getting into diffraction, which is going to account for some of the other things we were seeing with that double slit experiment. So, anyway, so lab. We're not going to do lab. I don't want to do lab with just the two of you, and I don't think the others are back yet.
They're not.
So we're not going to do lab on Friday. That's okay. Like this class, modern physics, there are not a lot of labs you can do. Right? We don't have like particle accelerators and fun stuff like that. So we'll have plenty of time to get all the labs done. It's just our labs now are going to be a little bit behind what we were talking about in class. So like next week's lab is going to be on lenses and mirrors. The week after that is going to be on double slit experiment. And so, right. So, but eventually we'll kind of get caught up.
So are we coming in on Friday?
So let's just plan on not. We'll worry about whatever once everybody's back. I'm not too stressed about time and all that. So,
Gotcha.
all right. But Diffie Hughes will still happen.
Alright, guys, subscribe to see more epic lectures from the Brewster.